Hello, welcome to the lecture on 1.4. Today we're going to talk about rational expressions. So first we need to do a couple of definitions. Start with the definition of a fractional expression. A fractional expression is the quotient of two algebraic expressions. Next definition. A rational expression is the quotient of two polynomials. All right, so what do these mean? First, I want to make a note. A rational expression is a fractional expression. So remember that if we had algebraic expressions here, a polynomial is a type of algebraic expression, which means that if we have a quotient of polynomials, we have a quotient of algebraic expressions as well, which would also mean that it's a fractional expression. Example, start with a x squared plus 1 over the square root of x minus 1. B, 3x squared plus 4x minus 1 over x squared plus 4. C, x squared plus 3x divided by 12 minus square root of x. And D, 1 over x squared. So we need to figure out which of these are rational expressions and which of these are fractional expressions. Now the difference between the two is the fact that a rational expression is a polynomial. A fractional expression has algebraic expressions in its numerator and denominator, or at least one of them is an algebraic expression. Here, the denominator is an algebraic expression that is also not a polynomial. So A is actually just an algebraic, or is a fractional expression. B, you have a polynomial in the numerator, polynomial in the denominator. This is rational. C, you have a polynomial in the numerator, but we have an algebraic expression in the denominator because the square root of x has a fractional exponent. The exponent on x is 1/2, therefore this is algebraic, not polynomial, so this is just a fractional expression. Here, 1 is a polynomial expression, x squared is a polynomial expression, so this is rational. Next, we're going to talk about the domain. Start with the definition. The domain is the set of numbers that the expression is permitted to have. Show you what I mean with an example. So we need to find the domain here. Let's find the domain of A, x squared plus 4x plus 4. B, square root of x minus 3. C, the cube root of x plus 4. While I realize that the definition of domain is the numbers that the expression is permitted to have, when we're looking for a domain, what we want to do is the opposite. We want to look for values that the expression is not allowed to take. For instance, here, is there any number that we cannot plug into x because the expression will resolve to an undefined value? No. Polynomials have domain all real numbers, as we'll see in a little bit. But we could plug anything in for x, any number in for x, and that number can be squared. Plug any number in, and we can multiply that number by 4, and then add all of the results. There's no number that we cannot plug in. So the domain here is all real numbers, because all real numbers are permitted. For part B, however, there are values that we cannot take. For instance, if I try to plug in x equals 0, I would get 0 minus 3, and then I have the square root of a negative number. But the square root of a negative number is undefined. It doesn't give us an output value, therefore, it's not permitted for this particular expression. We need to figure out all the values for which x minus 3 is non-negative. And I say non-negative specifically because, and this is a common mistake, so I'm going to write this over here. The square root of 0 is equal to 0. Remember what the square root means. The square root of a is equal to b if and only if b squared equals a. So the square root of a here, if a is 0, is going to equal b if and only if b squared equals 0. So we're looking for a number whose square is 0. Well, 0 squared is equal to 0. So b is 0 in this case. So the square root of 0 is in fact 0. So now that we've shown that we can actually have a 0 under the radical, we need to figure out where this is non-negative. So we need to know when x minus 3 is greater than or equal to 0. Because if it's negative, then the square root is going to give us an undefined value, and that value will not be permitted to be plugged in for x. So if we add the 3 over, we get x is greater than or equal to 3, and we're done. This will be our domain. Now here, are there any values that x cannot take? Now I need to note here that we have a cube root, not a square root. Remember, when you have an odd index on your radical, we can take negative numbers in the radicand. So let's say that x is equal to negative 5. Then we're looking for the cube root of negative 1. This works. The cube root of negative 1 is negative 1. So we can use negative numbers. So in this case, we actually have that the domain is all real numbers, because there are no values for which this expression will not be resolved to an actual number. I want you to try one. Find the domain. 3 over x squared minus x minus 20. And b, 1 over the square root of x minus 3. I will note that you need to be careful with these. There is a number we cannot divide by. You need to take that into consideration when you do both of these problems. Next thing I want to talk about is simplifying rational expressions. To simplify rational expressions, we cancel the common factors. Recall, a times c over b times c is equal to a over b. Now this comes from the numbers that we were talking about earlier, but it holds true for rational expressions as well, because, remember, x is holding the place of a number. So if we have something that looks like this, x plus 3 times x plus 2 divided by x plus 4 times x plus 2, then we can cancel the x plus 2's. Now that's because if we plug in a number for x, it would plug in for every single x value. Then that number plus 2 would be another number. And that number plus 2, whatever number that is, would be common on top and bottom. So we can actually cancel these. And this would resolve to x plus 3 over x plus 4. Let's do an example here. X squared plus 5x plus 6 divided by x squared minus 9. So what you need to do first whenever you're doing these problems is you need to factor. So let's start with the numerator and say x squared plus 5x plus 6. Let's factor this. So we need to find two numbers that multiply to 6 and add to 5. Now remember, because our a is equal to 1, once we find these two numbers, we can go straight to the factorization of this expression. If a is not equal to 1, then you have to go through the longer factorization process. Like here, two numbers that multiply to 6 and add to 5 is going to be 3 and 2. To check, 3 times 2 is 6. 3 plus 2 is 5. So this will factor into x plus 3, x plus 2. Now we do the denominator, x squared minus 9. And we need to find two numbers that multiply to negative 9 and add to 0. Now, if you remember from your factorization rules, the quick factorization rules, we have x squared minus 3 squared. So we actually have a difference of squares, and we can go straight to the end if we want to. But if you don't recognize that immediately, that's okay. We can just go straight into factorization. So we need two numbers that multiply to negative 9 and add to 0. Now, since they need to add to 0, we know they need to be the same number, but opposite signs. And then, of course, 9 is 3 squared. So we have 3 times negative 3 gives us a negative 9. 3 plus a negative 3 gives us 0. So this will factor into x plus 3 times x minus 3. If we look at this rational expression in its factored form, we get x plus 3, x plus 2, divided by x plus 3 times x minus 3. Now we can see that we have an x minus 3 on top and bottom, so we can cancel these. Because, as I stated before, when we plug in a number for x, we would plug it in for every x, but when we plug in a number for x, that number plus 3 will be a different number. But that different number will be common on top and bottom. So these two will cancel. Now I want you to try one on your own. Find the domain and simplify. I do need to note up here, the domain is still x is not equal to 3 and x is not equal to negative 3. The domain doesn't change because we look for the domain at the beginning. So here x cannot be 3 or negative 3 because we will get division by 0. And that's impossible. Dividing by 0 gives us an undefined number. So 3 and negative 3 are not allowed to be in the domain. Even once we get to the simplified version, negative 3 is still not in the domain of the expression. X squared plus 3x plus 2 divided by 2x squared plus x minus 1. So I need to note here as well, don't forget that our a is not equal to 1, so you have to go through the longer factorization process. If the coefficient of the x squared term is equal to 1, like the top, then you can do the short factorization process as I did here. The next thing I want to talk about is multiplying and dividing rational expressions. We multiply rational expressions just like we would multiply numbers. The numerators get multiplied together, and the denominators get multiplied together. Basically, we multiply straight across. Do an example of this. X squared plus 2x plus 1 divided by x squared minus 3x plus 2 times x squared plus 2x minus 3 divided by x squared plus 4x plus 3. Now we need to factor each of these terms. I mean, technically we don't have to in order to multiply, but if we're going to simplify the expression to its simplest terms, then we want to factor it so that we can cancel whatever we want, whatever we can. So let's start with x squared plus 2x plus 1. You might actually recognize this. And if you do, you can go straight to the end. If you don't, then we want to factor it using our normal factorization process, which will be two numbers that multiply to 1 and add to 2. And that will, of course, be 1 and 1. 1 times 1 is 1, and 1 plus 1 is 2. So we get x plus 1 times x plus 1, or x plus 1 squared. Next, we're going to do x squared minus 3x plus 2, which will be the denominator of the first fraction. We need two numbers that multiply to 2 and add to negative 3. So two numbers that multiply to 2 and add to negative 3, that will be negative 2 and negative 1. Negative 2 times negative 1 is a positive 2. Negative 2 minus 1 is negative 3. So this will factor into x minus 3, x minus 1. And again, we can go straight to the answer because the coefficient of the x squared term is equal to 1. If it's equal to a number other than 1, you have to go through a longer process that we outlined in a prior section. Now let's do the numerator for the second fraction, x squared plus 2x minus 3. We need to factor this, so we're looking for two numbers that multiply to negative 3 and add to 2. And that will be 3 and negative 1. 3 times -1 is -3. 3 plus -1 is 2. We can factor straight into x plus 3 times x minus 1. Again, because our coefficient on our x squared term is equal to 1. Now for the denominator of the second fraction, x squared plus 4x plus 3. Now this is a common type of problem where the c is 1 less than the b. We're looking for two numbers that multiply to 3 and add to 4. Whenever you see that the c, the constant term, constant coefficient, is 1 less than the x coefficient, then it's going to be 1 and whatever c is. 1 plus 3 is 4, 1 times 3 is 3. So we get x plus 1, x plus 3. Now let's rewrite each of these rational expressions in their factored form. So we have x plus 1 squared divided by x minus 3 times x minus 1 times x plus 3 times x minus 1 and x plus 1, x plus 3. Now you might see right away that we can cancel our x plus 3 here and here. And if you do that first, that's an excellent way to do it. That is probably the most efficient way, is to look to cancel before we multiply. But I'm going to go ahead and multiply first and say x plus 1 squared times x plus 3 times x minus 1, all divided by our denominator, which will be x minus 3, x minus 1, x plus 1, and x plus 3. This. Now we can cancel whatever is common on top and bottom. So we have an x minus 1 that's common top and bottom. So let's cancel those. We have an x plus 3 that's common top and bottom. So we can cancel those. And then we have an x plus 1 on bottom and an x plus 1 squared on top. Now remember, when the square is outside the parentheses like this means x plus 1 times x plus 1. So we can actually cancel one of those x plus 1s with the 1 in the denominator. This is the same thing as saying x plus 1 times x plus 1. So when we cancel this one in the denominator, this x plus 1 in the denominator, we're canceling just one of these. All that's left on the top is x plus 1, and all that's left on the bottom is x minus 3. And that will be it. Now, dividing rational expressions will be done in a very similar way. We do it using the same idea, where we divide using the same rules as if we were dividing numbers. So remember, when you divide a fraction, you take the reciprocal of the denominator and multiply. So this is the same thing as a over b times d over c. Note that we took the reciprocal of the second term here. And we get AD over BC. Simplify. 2x squared minus 3x minus 2 divided by x squared minus 1 divided by 2x squared plus 5x plus 2 divided by x squared plus x minus 2. Okay, so I need to make a note here. Whenever you see something that looks like this, where you have a compound fraction, we have a rational expression in the numerator and a rational expression in the denominator, you need to look for the long division bar, the longer division bar. These shorter division bars are referring to the numerator and denominator, and saying that the numerator is a rational expression and the denominator is a rational expression, and those two rational expressions are being divided. This is the same thing as saying 2x squared minus 3x minus 2 divided by x squared minus 1 times the reciprocal of the denominator. So x squared plus x minus 2 divided by 2x squared plus 5x plus 2, like this. And now we're going to look for the factorization of these terms. So start with 2x squared minus 3x minus 2. And we are looking for two numbers that multiply to a times c, which will be negative 4, are a times c, and add to b, negative 3. So two numbers that multiply to negative 4 and add to negative 3. And this will be negative 4 and 1. Now note that our a is not equal to 1. The coefficient on the x squared term is not equal to 1. So we have to go through the longer process. 2x squared minus 4x plus x minus 2. And that process includes breaking up your b term into two separate like terms. So we have a negative 4x and a positive x here. And those numbers come from here and here. Negative 4 is the coefficient here, and the 1 is the coefficient here. And then we group them, remembering that there needs to be an x in the middle, and we factor out whatever we can. In the first one, we can factor out a 2x, so all that's left is x minus 2. And in the second one, there's nothing that's like, so we can factor a 1 out. And we just get x minus 2. Now notice that we have an x minus 2 and an x minus 2 common between this whole term and this whole term. So we factor out that x minus 2. And in the first term, we're left with a 2x, and in the second term, we're left with 1. And that's it. So this would be the factorization of the numerator on the first term. Now the denominator is a difference of squares. To save time, I'm not going to go through that. But I will go through the numerator and the denominator of the second fraction. X squared plus x minus 2. And we're looking for two numbers that multiply to negative 2 rather, and add to 1. So two numbers that multiply to negative 2 and add to 1 will be 2 and negative 1. Noting that 2 times negative 1 is negative 2, 2 plus the negative 1 is 1. Look at this. Now this will factor directly because the coefficient on our x squared term is equal to 1. So this is x plus 2 times x minus 1. And that is the numerator of the second fraction. The denominator, now we have an x squared coefficient that is not equal to 1. So we have to go through the long process again. And here, we're looking for two numbers that multiply to 4 and add to 5. So two numbers that multiply to 4 and add to 5, that will be 4 and 1. 4 times 1 is 4, 4 plus 1 is 5. So this, we will have to go through the long process again, which is to break up the b term, 2x squared plus 4x plus x plus 2. And we group the first two and the last two, factor out what we can. We factor out a 2x again. And what's left here is x plus 2. Factor out a 1. And what's left is x plus 2. And then again, note that x plus 2 is common between this whole term and this whole term. If we think of this as an object, it's common between the two terms. So we can factor that out, and we get x plus 2. And all that's left in this first term is 2x. And all that's left in the second term is 1. So the numerator of the first fraction is 2x plus 1 times x minus 2. The denominator is a difference of squares. That will be x plus 1 times x minus 1. Times the numerator of the second term is x plus 2, x minus 1. And the denominator is x plus 2, 2x plus 1. Now this time, I'm going to cancel what I can. You can even cross cancel here. Because we're multiplying straight across, I can cancel things that are in the denominator of the first fraction and the numerator of the second, or vice versa, the numerator of the first and the denominator of the second. Here, x plus 2, they're both in the same fraction, so they can cancel very nicely. We have an x minus 1 here and an x minus 1 here, so these two will cancel as well. And we have a 2x plus 1 here and a 2x plus 1 here, so these also cancel. And we are left with x minus 2 divided by x plus 1. Okay, I want you to try one. This one is to multiply the rational expressions and simplify. And we will have x squared minus x minus 6 divided by x squared plus 2x times x cubed plus x squared divided by x squared minus 2x minus 3. And be careful with these two. These are not going to be factored in the same way that you're used to factoring. You'll have to factor something out that's common. The next thing we're going to talk about is adding and subtracting rational expressions. To add and subtract rational expressions, we must find a common denominator. So an example here. Suppose that we have x divided by x plus 1 quantity squared plus 2 over x plus 1. Okay, so these two fractions do not actually have a common denominator. They're close. We have an x plus 1 in both, but we have two x plus 1s in the first one. Remember that x plus 1 quantity squared means x plus 1 times x plus 1. So what we need to do is we need to multiply the second fraction by x plus 1, top and bottom. And we do this because this is really just multiplying by 1. Because x plus 1 divided by x plus 1, these two would cancel, and we're multiplying this by 1 in general. Now remember, 1 is the multiplicative identity, therefore 1 times anything is that anything. It doesn't change anything. So we're not changing the value. That's kind of the point. We don't want to change the value, we just want to change how it looks. So we end up with x over x plus 1 squared in the first one, and 2 times x plus 1 divided by x plus 1 squared in the second one. Now we have a common denominator, x plus 1 quantity squared, x plus 1 quantity squared, so we can add straight across in the numerator. Now remember, when we add fractions, the denominator does not change. It's a common denominator. We get a common denominator because it doesn't change here. So we got x plus 2x plus 2. I also distributed my 2. That's how I got 2x plus 2 divided by x plus 1 quantity squared. And then we add the like terms, and we get 3x plus 2 in the numerator and x plus 1 quantity squared in the denominator. Now I want you to try one. Add the rational expressions. X over x squared minus 4 minus 2 over x squared minus x minus 2. Okay, so my hint here is that you need to factor the denominators. It will help you figure out what your common denominator needs to be. Next is compound fractions. Definition. A compound fraction is a fraction in which the numerator, denominator, or both contain fractions. So an example of this will look something like this. 1 plus x to the negative first power divided by x squared minus x to the negative 2. So it might not look like it's a compound fraction, but it is. I want to make a note over here on the side, very quickly, that 1 plus x to the negative 1 over x squared minus x to the negative 2 is not equal to 1 minus x squared over x squared plus x. What I mean by this is, because we have a negative first power, it doesn't mean that this goes to the denominator like we have seen before. In the previous examples, where an x to the negative first power would go to the denominator is when it's multiplying by the rest of the numerator. Here, it's not multiplying, we're adding to 1. Whenever we have a fraction like this, where we have a sum in the numerator and a sum in the denominator, we have to think of it as if the numerator and the denominator are in parentheses. Thus, they get resolved before any sort of multiplication, or even exponents. So the exponent will not move this to the denominator of this entire fraction. It'll move it to the denominator of a fraction in the numerator. That looks like this. Because these are being added, respectively on the bottom and top, when we resolve the negative power, that negative power will push it into the denominator of its own fraction. Now what we want to do is we want to make sure that this is no longer a compound fraction. We want to simplify this to the point that it's exactly one polynomial divided by another polynomial. Okay. So here on top, we need to find a common denominator between 1 over x and 1. So we multiply the 1 by x over x. Again, x over x is 1, and 1 is the multiplicative identity. So I'm not changing the problem, I'm just changing how it looks. Similar on bottom, we want to find a common denominator between x squared and 1 over x squared. So we multiply top and bottom of x squared by x squared here, like this. Now remember, x squared is over 1, so is 1. 1 is also over 1, but it doesn't really matter. So we would end up with x over x plus 1 over x in the top, and in the bottom we would have x to the 4th over x squared minus 1 over x squared. Now this then means that we can add the two fractions on top and add the two fractions on bottom because we have a common denominator of the respective fractions. So we get x plus 1 over x, and on the bottom we have x to the 4th minus 1 over x squared. Now we have a fraction, a rational expression, divided by another rational expression. So remember how we resolve that. When we resolve a rational expression divided by another rational expression, we take the reciprocal of the denominator and we multiply. And again, that comes from the fact that we're really just multiplying by 1 top and bottom of this big fraction. So here, if we look at it a little bit differently, I'm going to do this in blue so that we can see it a little better, hopefully. So we would have something like this. What we're actually doing is multiplying top and bottom of the big fraction by this. X squared over x to the 4th minus 1 divided by x squared divided by x to the 4th minus 1. Notice that the numerator of this fraction is the same as the denominator, so really I'm just multiplying this entire fraction by 1. It's just a clever representation of 1. And then we multiply straight across, and when we multiply straight across in the bottom, we get full cancellation, which would mean we would end up with 1 divided by 1. So our entire denominator becomes 1. In the numerator here, we get x squared times x plus 1 divided by x times x to the 4th minus 1. Now, in order to simplify this, we can cancel x's, but in order to actually complete the simplification, we need to factor this. And you might look at that and say, well, I don't know how to factor this. You do. This is still a difference of squares. It's just x squared squared minus 1 squared. So x to the 4th minus 1 is the same thing as x squared squared minus 1 squared. You might be able to see it now. This would be a squared minus b squared. So our a is x squared, our b is 1. This will actually factor into x squared minus 1 times x squared plus 1. And then we can further factor this x squared minus 1 using a difference of squares again into x plus 1, x minus 1. Now the x squared plus 1 doesn't actually factor, so our fraction actually becomes, if we cancel the x in the bottom and one of the x's in the top, before we actually factor, then we have x plus 1 divided by, or x times x plus 1, sorry, divided by x plus 1, x minus 1, x squared plus 1. And then we can cancel here x plus 1 and x plus 1. We simplify further to be x over x minus 1, x squared plus 1. All right, I want you to try one now. Simplify the following fraction. X minus x over y divided by y minus y over x. Okay. I want to do one more example like this because this is a very odd example. This is not a rational expression because we have square roots, but I want you to look at this and see how we would actually solve the problem. Suppose we have something like this, 1 minus x squared to the 1/2 power plus x squared times 1 minus x squared to the negative 1/2 power divided by 1 minus x squared. I want to simplify this. First, notice this is not a rational expression, it's a fractional expression. Because we don't have polynomial in the top and a polynomial in the bottom. We only have a polynomial in the bottom. The top we have the square roots. So this is not a rational expression. But we've done stuff like this before where we factored, and we factored out the most negative rational exponent. So what I want to do is I want to factor out a 1 minus x squared to the negative 1/2 power. Okay. Note that this is 1 minus x squared to the 1/2. So when we factor out 1 minus x squared to the negative 1/2, we will be doing an operation like this. 1 minus x squared to the 1/2 divided by 1 minus x squared to the negative 1/2. Now remember, when you have the same base, and we do have the same base, you subtract exponents when you divide. So 1/2 minus a negative 1/2 is a positive 1. So in this first term, we end up with 1 minus x squared. And in the second term, we just have x squared. And the denominator hasn't changed. But then we can simplify this a bit. First, we have a negative 1/2 power. Now this is being multiplied by the entire numerator, the entire rest of the numerator. So we can actually move it to the denominator. Now remember what I said before, we can't necessarily move things to the numerator or denominator. We can here because it's all in the multiplication step. So when you're doing your order of operations, we would resolve our parentheses, we would resolve our exponents and everything. But the parentheses here are not affecting this because it's multiplying. This is not included in any parentheses. It's not being summed to anything. It's not being added to anything. So I can actually I can resolve the negative exponent first and push it to the denominator. And we end up with 1 minus x squared plus x squared will just be a 1 divided by 1 minus x squared times 1 minus x squared to the 1/2. Or if you want, you can write it as 1 minus x squared to the 3/2 power. Noticing that we have a 1 power here and we have a 1/2 power here, and the base is the same. 1 minus x squared is your base. All right, the last concept I want to go over is rationalizing the denominator or numerator. So first I want to recall something. This plays a very big role. The difference of squares, a plus b times a minus b, is the same thing as a a squared minus b squared. This is a difference of squares. A squared minus b squared factors into this, but remember, equality holds both ways, so we can multiply these to become a squared minus b squared. Notice that both terms are squared. This is important when we're trying to rationalize. Suppose we want to rationalize something that looks like this. 3 over 2 plus the square root of 5. Then our problem is that if we try to just multiply by 2 plus the square root of 5, because of the distribution property and foiling everything out, we would end up with a radical. But because we have a difference of squares, all we need to do is multiply by the conjugate. 2 minus the square root of 5. We change the sign and multiply. So we end up with something like this. Now notice on bottom, a plus b, a minus b. So if we had 2 as our a and square root of 5 was our b, when we multiply these, on top we would end up with 3 times 2 minus square root of 5. We do not need to distribute the 3 if we don't want to. But in bottom, because of the difference of squares, these two will multiply to a squared minus b squared, where our a is 2 and our b is square root of 5. So we end up with 2 squared minus the square root of 5 squared, which is equal to 3 times 2 minus root 5 divided by 4 minus 5. Now, to resolve the negative 1, you just change the sign. I want you to try a couple here. I want you to rationalize the numerator on this problem. Now, this plays a very big role later on in mathematics, this square root of 9 plus h minus 3 over h, where 3 and 9 are not really special. There's a relationship between 3 and 9. Hopefully, you'll see it when you do this problem. But overall, those numbers are not special, just that relationship is. Rationalize the denominator. Now, I will say that this problem is very challenging. I will note that the index on the radical is 3, so you can't use the difference of squares in this problem. You need to use something else. And you might have to think a little bit to maybe go back in your notes or go back in the lectures and try to find something where we can eliminate a radical with an index of 3. There's a lot of common errors that come up in this type of these types of problems. Specifically, a plus b quantity squared is not equal to a squared plus b squared. Remember, a plus b quantity squared means a plus b times a plus b. And you have to distribute twice in order to actually multiply this out. It ends up being a squared plus 2ab plus b squared, which is clearly not a squared plus b squared. A very similar problem, the square root of a plus b is not equal to the square root of a plus the square root of b. This is easily disprovable. The square root of a plus b does not actually simplify. Let me show you how to disprove this. Let a equal 9 and b equal 16. Then on the left here, we would have the square root of 25. And on the right, we would have the square root of 9 plus the square root of 16. Square root of 9 is, of course, 3. The square root of 16 is, of course, 4. 3 plus 4 is 7. And on the right, we would just have 5. So as you can see, that the square root of a plus b is not equal to the square root of a plus the square root of b. 1 over a plus 1 over b. This might seem obvious, but these errors happen a lot. This is not equal to 1 over a plus b. Remember, you have to find a common denominator. So here, the common denominator would be ab. So we would need to multiply top and bottom of the first fraction by b and top and bottom of the second fraction by a. So we would end up with a plus b divided by ab. But these are common mistakes. This type of stuff happens all the time. Another one, a plus b divided by a is not equal to b. Now this one's a lot more common. People will try to cancel these a's. Now, you need to think about why this is not possible, why we cannot do this. We can't do this because, as I stated before, you have to think about the numerator and the denominator being in parentheses. Now, we have a plus b, so this sum needs to be resolved before we can divide by a. So if you plug in numbers, 3 plus 5, for instance, you would have 8 divided by 3. That's not the same thing as 3 divided by 3 plus 5. Okay? Now, you can actually split this. You can rewrite this as a over a plus b over a. Because we have a common denominator, these two would add, the numerators would add, and the denominator would stay the same and give us this. Then you can reduce this, if you want, to be 1 plus b over a. And that's okay. But this is not. This is a common mistake that happens all too often. That will be it for today. I will see you all in the next lecture.